Hello, we're going to quickly go through all the directional derivative questions that have been asked in the past couple of years on exam ones and finals. So we know for a directional derivative, it's going to be made up of our gradient vector, and we're going to take the dot product of whatever this gradient vector is with the unit vector in the direction that we're pointing. So in the case of our first problem here, we can find these pretty quickly, and we'll see that a lot of these problems are very, very quick to go through once you get the general form that they take. So our gradient vector is going to be composed of our partial derivative with respect to x and our partial derivative with respect to y. So let's find those. Well, fx is going to be e to the y squared plus e to the x plus y, and f of y is going to be 2xy e to the y squared plus ex plus e to the x plus y. And then we know we have to evaluate this at the point that they are having us evaluate everything at, and that will give us 2 and 1. And so we know that our gradient vector is 2, 1. That will be the direction of greatest ascent. That's another way they can ask some of those gradient questions, but in this case, we have to go one step farther in finding our unit vector of the direction that we're pointing in. So in this case, you can take a nice little shortcut and realize that 3 and 4 are part of a Pythagorean triple. So 3 squared plus 4 squared is 5 squared. So our unit vector in this case is going to be 3 over 5 and negative 4 over 5. So taking this dot product, we will get 6 over 5 minus 4 over 5, which is 2 over 5. And we're done. Okay, here we're finding the directional derivative of a function at this point pointing in this direction. So taking the same steps as before, we need an fx and an fy. Let's find those quickly. We will get, let's see, 4x over root 4x squared plus 3y for fx, and we will get 3 over 2 root 4x squared plus 3y. And we're evaluating this at 2, 3. This will give us 8 over 5, and this will give us 3 over 10, which we can put in this. We can put these in the same form. This is 16 over 10, and this is still 3 over 10. And you'll see why putting everything in with the same denominator will be helpful later. So now we know that we're pointing in the direction I comma negative 2j, so that's going to be 1 comma negative 2. And when we find that unit vector, we will get 1 over root 5 comma negative 2 over root 5. And so now taking our dot product, let's move things down here. We're dotting this with our gradient vector that we found up here. So 8 over 5, this is not the gradient vector. This is our gradient vector. Our gradient vector is going to be 16 over 10 and 3 over 10. And this dot product will give us 16 over 10 root 5 minus 6 over 10 root 5, which will give us 10 over 10 root 5, or just 1 over root 5. Okay, same thing. As you see, they really, don't have many other ways of asking these questions, which is good for us. We're looking for this directional derivative. Although this one has a little bit of a trick. We don't know just offhand what the direction vector is that we're dealing with, so we have to do one little tiny step in there to find it, but let's not worry about that yet. We need, well, it's not really f, it's t of x and t of y. Let's find those. T of x is going to be negative y minus 1 over x minus 2 squared, and ty, if I move this up a little bit, we'll have more space. Ty, well, we can split the original function up into y over x minus 2 and that all minus 1 over x minus 2. And taking x to be a constant, taking a derivative with respect to y is going to completely get rid of this section, and this y is just going to become a 1. So ty is 1 over x minus 2. So now, plugging in 3 and negative 2, let's see what we get, and I'm going to need a little bit more space in here. This will be 3 over 1, and this will be 1. Okay, so what is our direction vector? We are sitting at 3, negative 2, and we can graph this out, sometimes helpful. 3, negative 2, right about there. We want to point in the direction of the origin. Well, the position vector that we're dealing with right now is the one that points from the origin to this point. So all we have to do is flip the signs of this position vector here and find our unit vector. So our direction vector will be negative 3, comma 2, and the magnitude of this will be 13. And so all we have to do is divide by root 13, and take our dot product with this over here, compress it a little bit, with 3, comma 1. And this dot product will be negative 9 over root 13 plus 2 over root 13, which will give us negative 7 over root 13, and we're done. Okay, the directional derivative of this guy at this point in this direction is what? And interestingly here, we're dealing with a function of 3 variables, and we're going to have to find, as you'd expect, an fx, an fy, and an fz. But other than that, nothing is different. We're using the exact same methods that we always do. There's just one more variable that we have to deal with, which in a way is one more, area where error can be made. So fx, well, e to the x, we treat everything else as a constant. This will just be y squared e to the x minus z. Fy will be 2y e to the x minus z. And fz will be negative y squared e to the x minus z. So now evaluating at the point 3, 1, 2, well, this is going to be 1 squared e to the x minus z, which is just going to be e to the 1. So all of these are just e to the 1, e to the 1. And we have a 2y here, that's going to be 2. And we have a negative y squared here, which is going to be negative 1. So overall, our gradient vector at this point is e, 2e, negative e. Okay, perfect. So our direction vector that we're pointing in, that we want to find the directional derivative of, well, in that direction, is 2, 5, 1. The magnitude of which will be 4 plus 25 plus 1, which is root 30. So we can divide everything in here by root 30 and take our dot product, bringing this guy down here. And let's see what we get. We will get 2e over root 30 plus 10e over root 30 minus e over root 30, which will give us 11e over root 30, and we're done. Okay, this is as far as these directional derivative questions go, this is a hard one. It's not clear from the start because of the kind of more specific, less theoretical context that they put the problem in. It's not clear right away, that a directional derivative is really what we're looking for here. But if we read it out, we will find that all of the same ingredients are there that we're used to seeing in these questions. So the depth of the lake at a point xy is that. So this is the depth of a lake is analogous to whatever function, whatever we're getting out of any of these functions here. So this guy, this f of x, y, z could be modeling something like the cooling of a metal after it's in contact with a heat source or something. It doesn't really matter what it's modeling as long as we can express it in terms of a function. So f of x, y, they're saying that that's equal to 3x squared y plus 5y squared. Okay. So that's good. We've got half of what we need. All we need now is the point that we're at and the direction vector in order for this to be a solvable directional derivative question. They say assume that x and y are measured in miles. Okay, we really don't care. It's all of our answers here have the same units, so it's slightly useless to know that. If a boat at the point 2, 1, okay, so there's our point. We're actually at f of 2, 1. Let's just note that is sailing in the direction of that 3, 1. So f at 2, 1 in the direction of 3, 1. At what rate is the water depth changing? Okay, so that's all the ingredients we need to call for a directional derivative. So let's find fx and fy, and then our unit vector, and let's take a dot product. So this will be 6xy, and fy is going to be 3x squared plus 10y. Evaluating at 2, 1, we will get 12, and we will get 10 plus 12, so 22. And then finding our unit vector, the magnitude of 3, 1 is going to be root 10. And so our entire expression is going to be 12, 22, dotted with 3 over root 10 plus, oh, whoops, not really plus, 1 over root 10. And this dot product is going to be 36 over root 10 plus 22 over root 10, which is going to be 58 over root 10. And they want a rate of change, and in this case, the units for this is just feet per mile. Okay, finally, we have the directional derivative of, another function that takes 3 variable inputs, x, y, and z, at this point in this direction. So there's a very easy way to mess up these questions. It's less obvious. It's a harder trap to fall into in some of these other questions, especially if they give you a direction vector itself. Because what this notation is saying is we're at the point 2, 1, 2, 1, and we're pointing in the direction 3, 1 over here. So 3i plus j. But what this question is saying is we're at the point 1, 2, 3, and we're pointing towards 3, 1, 5, and both of these measures are with respect to the origin. And so, sorry, I actually drew that very misleadingly. We are at this point, and if we move this over a little bit, it'll be more clear. This is saying we're pointing in this direction. So we're saying there's this thing over here, and we're pointing at that to tell you where we are. And instead of saying from that point we are pointing here, we're saying, oh yeah, and we're also pointing over here. So what we need is to disregard the position vector that we had here and make a new position vector with respect to our first point. So sorry if that's confusing at all. That's just a very complicated way of saying we need to find the vector that points from the point that we're at to the point of interest instead of using this as a position vector, because we will get the wrong answer. So proceeding normally, fx is going to be 2xy, fy is going to be x squared plus 2yz, and fz is going to be y squared, which will be 4. Up here, this will be 1 plus 12, so 13. And this guy right here is going to be 4. Okay, perfect. So our gradient vector is 4, 13, 4, and we are dotting that with the unit vector of the position vector that points from 1, 2, 3 to 3, 1, 5. So how I always think about this in my head is how many units do we have to travel up and down to get up or down to get from whatever coordinate we're dealing with to the coordinate we want to finish at. So in terms of our x coordinate, we need to go up by 2 from 1 to 3. So our position vector, our second position vector, is going to be 2, comma, -1, comma, 2. Perfect. So the magnitude of this guy is going to be 4 plus 1, which is 9. Square root of 9 is 3. So 2/3 minus 1/3, and then another 2/3. So this dot product will give us, if I fill everything in here, this dot product will give us 8/3 minus 13/3 plus 8/3, which will simplify down to 3/3, which is 1. And we are done. Hopefully this was helpful. Let me know if any of my answers were wrong, and I will go back and fix them.